In this video we're going to look at conjugate points, and we're going to try and get an intuitive understanding of them, and also introduce the idea of envelopes. So let's go back to the basic problem we had. We're trying to find out the sign of the second variation. Now what we did was we knocked the second variation into this general form here. So that means that epsilon squared is obviously going to be positive because it's squared, and that's a factor 2, which is a positive value. If we ensure that this thing in here inside the brackets doesn't equal 0, then it's a squared term, so that's going to be positive as well. So it means that the value of I2, the sign of it, is going to be determined completely by the value of this f11. So if we ensure here that this term here doesn't equal 0, then we can say that if f11 is greater than 0, then we've got a local minimum, and if f11 is less than 0, then we'll have a local maximum. Now one of the previous videos we've seen that in order to ensure that this term here doesn't equal 0, what we have to do is we have to ensure that this u of x doesn't vanish anywhere within these limits a, b. Now the points where u of x vanish are called the conjugate points. So that point a dash is conjugate to that point a. Now this little description here doesn't really show the full geometric beauty of the idea of conjugate points and the idea of envelopes, so we're going to have a look at a couple of examples here that will describe it and a little bit better. Excuse me. So let's imagine we have a sphere. Now if we have 2 points in a sphere, a and a dash, and both of them are diametrically opposite, so that's just the large arc that goes all the way around. Then if we were to draw another arc all the way around this sphere, then it must, and it passed through point A, then it would also pass through point A dash, and we could draw an infinite number of these arcs all the way around this sphere, and if each of them passed point A, then they must all pass through point A dash as well. So this point A dash is the conjugate of A, and this is a nice kind of graphical representation of what we have above, because if we were going to travel from A to some other point B on one of these arcs, then we have two options to do that. What we can do is we can travel all the way around this way, and we can go through the conjugate point A dash to get to B, or we can take the short route from A to B. Now that's really what we're showing up here. If we were to go from A to B without passing through the conjugate point A dash, then this here would be the minimum path, or the path would be an extremal. If we were to go in the opposite route around here, which is equivalent to passing by this A dash, then this route here wouldn't give us an extremal. Now let's have a little look, and we'll look at another example here, an example of a projectile. So if we were at point A and we had, say, a cannon, and we were firing at a constant velocity and then just changing the angle at which the cannon fired, then we would have these yellow curves here. So this would be the path that the cannon would take, and it would be an extremal. Okay, and if we were to change the angle, then it would go in a different path here, and again change the angle, it would be a much steeper path. And if we were to face the cannon straight up, then the cannonball is just going to go straight up and then it's going straight back down again, and we can turn it round and we can go the other direction as well. Now if we would do that for all lots of different angles, then we would notice that these parabolas here, which are the extremals, they would be contained within one big envelope, which is in blue, and this would be a parabolic envelope, and that would be called the parabola of safety. And you could understand that because if you were outside this blue parabola, say you're out here somewhere, then they will never ever be able to hit you with that cannonball. Now it turns out that, and what we'll see down below as well, is that if this is a point A, then if we take the tangents to these extremals, and if we take the point where the extremals meet these envelopes here, this envelope, then that point there will be a conjugate point to A. And of course there's another conjugate point to A up here, and another conjugate point, and there's an infinite number of conjugate points all the way around this envelope. So we can say that that point A has all of these values A dash as conjugate points. Now let's have a look, and we'll look in a bit more detail mathematically about how this is held together, and the ideas of how conjugate points are related to extremals and related to envelopes. So if we had one solution of the Euler-Lagrange, so the solution we've seen before is of the form S of x C1 C2, where x is your independent variable, C1 and C2 are your parameters. So all solutions to the Euler-Lagrange are of this general form, so we call that equation 1. Now let's imagine we took another extremal which is close by to this one here, so that's another solution that's close by, and we call that solution, it's going to be S of x C1 comma C2, that's meant to be a comma C2, and then we add on this little variation here, so the little variation is going to be alpha u of x, okay, where u of x is a solution to that accessory equation. Then we can see that these two extremals are going to be intersect, in fact they're actually going to be equal whenever the u of x equals 0. So when u of x equals 0, we know that this thing here is just going to be equal to this thing here. So it's going to vanish, and we let this thing u of x vanish at some point A. Okay, so for example up here it's going to be this point A here, or in the example it would be here, or example up here the u of x vanishes at that point A there. Now we also know that the only other place where u of x is going to vanish is at this other point A dash, which is going to be our conjugate points. So it would be this A dash here, or all of these A dashes here that cover this envelope. Now if u of x vanishes at all of the points, and it vanishes at all of the points conjugate to A, so that's all the points A dash, then what we can do is we can also write this thing here, these are two equations here, we can write it out in a different form. We can say let the first extremal be written here, the same as equation 1, but we could rewrite the variation here in a different format. So we could write that there as taking a small variation in one of the parameters, so you could say that as a function of x and some delta C1 comma C2. But this value variation y is dependent on this C1. Okay, so it means that you can write that variation out quite simply as the change in y with respect to C1. The change in y with respect to C1 times a small variation in C1. Okay, it's an equivalent thing. Writing that and writing this is the same thing. But here's the coup de grace, and there's the interesting part. From the previous video, we've already seen that this delta y upon delta C1, well, that is a solution of the accessory equation. Okay, you'll see that in the last video if you're just going to have a look at that if you're unsure. So it means then that if delta y upon delta C1, which is a solution to the Jacobi accessory equation, we'll call that solution, that particular one, u1x, so it's going to vanish at a point A, and it's also going to vanish at all the points conjugate to A. So equivalently, what we can say is that if this equation 1 and equation 2, if these are going to intersect, then they're going to intersect at point A, and they're also going to intersect at all the points conjugate to A. So that means really then what we're saying is that all the points, and this is the main point here of the video, all the points conjugates of A, they are all limiting points of the neighbouring extremals passing through A, and they form an envelope of extremals, and that can be seen quite simply in geometrically up here in terms of the canon. If we were to look at this one extremal here, and we were to put in another extremal, I'll just pop it in a different colour here for us. If we were to put in another extremal which is close by, okay, another extremal close by here, then which would come down. So in effect, in this instance here, this example, we would be changing the angle of the canon. So let's make the angle just a little bit steeper, and it would come up, and it's going to come down somewhere down here. Okay, then if we were to take the limit as this angle tended towards 0, then this extremal would tend towards the blue extremal would tend towards the yellow extremal, and that would just tend towards a point here, which would be the conjugate point. Okay, so that's as much as we want to talk about in this video. We're still in the position where we don't know how to find these conjugate points, unless of course that's geometrically it's a very simple problem. So in the next video we're going to derive an analytic method for finding the conjugate points. I hope you enjoyed this video. If it was of use, then please don't forget to subscribe and also leave some comments, and I'll catch you on the next video. Goodbye.